introduction. So this is Water Week, guys, for the Cross UIFL seminar. We're going to be talking about flooding, other hydrologic concerns. And we're really young. We're really lucky to have Sunyoung Park and Ethan Coon presenting. I'm just give them a quick intro for both of them, and then we'll let them take it away. And so Sunyoung Park is a PhD student in the Department of Civil and Environmental Engineering at the University of Illinois, Urbana-Champaign, where she's co-advised by Marcelo Garcia and Steve Nesbitt. And she is doing a concentration in computational science and engineering within the Department of Climate, Meteorology, and Atmospheric Sciences, focusing on understanding multi-scale interactions between atmospheric, hydrologic, and hydraulic processes to understand uncertainties in extreme rainfall and subsequent flooding in Chicago. So we're going to get to hear about her work, and I'll just quickly introduce Ethan too, so I don't need to interrupt midstream. So Dr. Ethan Coon from Oak Ridge National Labs, computational hydrologist in the Climate Change Science Institute. And his background comes in applied computational mathematics. His research includes computational methods, especially focusing on Earth's land surface and subsurface processes, and does a lot of work across subjects ranging from modeling, data integration into models, and using models to understand processes under global environmental change. Ethan has degrees from University of Rochester in applied mathematics and his PhD from Columbia, if I remember that correctly. So with that, I will hand it over to Sunyoung. Please take it away.
Do you see my screen?
We do. It looks great.
Yeah, thank you for the introduction, and thank you all for the opportunity to share my research with you today. In this presentation, I'll be discussing flood risk management in Chicago, focusing on challenges of urban flooding and how we can enhance our flood response. So let's start with a view of downtown Chicago, looking down the Chicago River from the Michigan Avenue Bridge. And today, the bank of the river are well defined and with buildings constructed right up to the water's edge. And the river itself has been widened and deepened and sits significantly lower than the surrounding landscape. But if you look at the two pictures of the same area, we can see just how much things have changed. In the top image, taken from above the Harrison-Denver Creek, one of the drinking water sources for Chicago from the Lake Michigan, we see the modern skyline along the river. In contrast, the bottom image shows Chicago as it looked in 1820. Here we can still see the natural state of the Chicago River with its north branch and south branch and main stem from flowing into Lake Michigan. The banks are undefined and reflecting the river's original state before urban development transformed it. And as Chicago's population grew, so did the need for infrastructure. By 1857, the city's population had surged to 93,000, and by 1868, the Chicago River was home to one of the busiest ports in the world. This rapid growth necessitated a way to manage rainwater and wastewater, and so in the 1850s, Chicago began work on its sewer system. This map shows the early stages of what would become the first comprehensive sewer system in the United States. And the sewer were designed with two main purposes, to drain rainwater and to carry sanitary sewage from homes and businesses directly into the river. Since wastewater treatment technology didn't exist at the time, so this system relied on a river to dilute and carry away waste. Originally, the Chicago River flowed naturally into Lake Michigan. This connection between the river and lake seemed logical at first, but as the lake could help dilute the sewage, but as the population grew, this natural flow started presenting significant issues for the city. A key factor here is a landscape of natural flatness. Water flows downhill, but Chicago, the river flows through a very flat area with only a slight elevation difference between the river and the Lake Michigan. With no substantial slope, the river flows very slowly towards the lake. This flat terrain, combined with the interaction of sewage from growing city, created problems. The slow-moving river carried sewage into Lake Michigan, the very source of cities' drinking water drawn through intake creeks located a couple of miles offshore, just north of Navy Pier. Just west of the city lies a watershed boundary, essentially high point in the landscape where water flows downhill on either side. Um, yeah, this watershed boundary divides two of North America's major watersheds, the Great Lakes watershed, which drains northward to the Atlantic Ocean via St. Lawrence River, and the Mississippi River watershed, which drains south to the Gulf of Mexico. Chicago sits right on the line between these two watersheds in some areas, such as Chicago. This boundary is barely perceptible, while in others it's more noticeable. Now that we understand Chicago landscape, despite early sewer system, the city continued to struggle with flooding due to flat terrain and poor drainage. To help address this, some part of city were even raised to improve separation between the river and urban areas, but the flooding remained a persistent issue. On top of this, the flow of untreated sewage into the river created pollution that threatened Chicago's drinking water intakes, and a solution was urgently needed to both manage flooding and prevent lake contamination. In 1889, the Metropolitan Water Reclamation District of Greater Chicago was founded with a monumental goal to reverse the flow of the Chicago River, and the aim was to improve drainage for the city and protect Lake Michigan from pollution. To accomplish this, engineers excavated a canal across the watershed boundary, connecting the south branch of Chicago River to the Des Plaines River at a lower elevation in Rockport, Illinois. So this shift created a downhill slope that directed the river away from the lake, providing drainage and redirecting pollutions. Yeah, here's an incredible history photo from 1896 that shows construction on Chicago Sanitary and Ship Canal. The level of detail is remarkable, and you can see workers and even horse giving a sense of scale to this massive project. Today, the Chicago Sanitary and Ship Canal remains an essential waterway. Here's a view looking northeast toward downtown, and moving south to the confluence of Sanitary Ship Canal and the Columbus Sac Channel. And Chicago's population continued to grow rapidly, reaching 2 million by 1910. And publicly, water quality became a major issue as untreated sewage polluted into public creek. So today public creek still exists, though and modern wastewater treatment now diverts a sewage to treatment plants where it's clean before release. So the Chicago area now operate a vast waste treatment network to protect water quality. MWRD service area covers 375 square miles served by combined sewer systems. And the tunnel reservoir plan, or TARP, specifically address combined sewer areas. Under normal condition, intercepting sewer carry both rainwater and sanitary sewage to a treatment plant, but during heavy rains, the system can become overwhelmed and leading to the combined sewer overflows, where excess water flows back into the river. And these overflows not only pollute the river, but can increase flood risk by adding to the water volume in waterways. So the MWRD and City of Chicago and Cook County form a flood control committee to address this issue. And the solution was TARP project underground network of tunnels hundreds of feet below the surface and designed to capture this overflow and prevent pollution. And the water is held until treatment plant can catch up, then fully treated before released into the river. This is my advisor, Marcelo. He and his team provided hydraulic modeling framework for the project and developed MetroFlow to analyze performance of the main stem and Desplain deep tunnels and the McCook Reservoir. And also reservoir developed the Illinois urban hydrologic model and implemented for the Calumet TARP system. So TARP includes 4 tunnel systems that follow the course of the river they protect, and the tunnel connect to the sewer system through drop shaft, which funnel excess water down into the deep tunnel system. And each drop shaft has 2 sections, one for water to flow down and another to allow air to escape, preventing air pressure buildup in the tunnel. So this is the McCook Reservoir. And McCook is being completed in stage 1 with the capacity of 3.5 billion gallons, has been operational since 2017, and stage 2 under construction will bring the total capacity to 10 billion gallons. So together with the Thornton Reservoir, which has a capacity of 7.9 billion gallons, TARP will ultimately hold 75 billion gallons. And this is a capacity that could fill over 318 million rain barrels. Despite Chicago's extensive flood management system, the city still faces serious flood risk from both surface water and sewer backups. With heavy storms becoming more frequent and intense rainfall often outpaces the capacity of local sewers, which were designed for much smaller flows relative to Chicago's current population density. And recent example took place in early July last year, when central Cook County received up to 9 inches of rain over an 18-hour period. So this extreme event was classified as an 1 in 100 chance storm with a 0.2% probability in any given year. So as a result, this particular storm caused significant flooding across many areas, and major roadways like I-290 were inundated, underpasses were overrun, and over 70,000 basements flooded. And only damage estimate approached 500 million, underscoring the significant impact of this high-intensity storm. This example highlights the challenges Chicago faces as aging sewers and increasing rainfall continue to test the limit of even the most advanced flood control measures. Modeling flood risk in a city like Chicago prevents unique challenges due to the complexity and scale of its combined sewer system. This system operates on multiple layers, starting from surface catchments and moving through local sewers and interceptor sewers, connecting structures, waterway, deep storage channels, and finally to large storage reservoirs. Accurate hydrologic modeling across this different spatial scale is crucial for assessing and managing urban flood risk. However, the sheer size and complexity of Chicago's infrastructure and hydrologic processes make modeling particularly challenging. Capturing the detailed interactions between surface runoff, sewer flow, and storage capacity is vital but computationally intensive. To address this challenge, we need to simplify models strategically and streamlining components where possible while still maintaining essential dynamics. So this balance is key to creating practical and feasible models that can provide reliable flood risk insights for such a large and intricate urban environment. In large scale urban flood modeling, the high detail models can be computationally intensive and may not be feasible across the entire area. So different scales require different levels of detail, and applying the same modeling approach everywhere isn't practical. So hydrologic processes and also the hydrologic processes are interconnected across scales. So effective models need a feedback mechanism to capture this interaction. So to address these challenges, we implemented a nested modeling approach. Core scale model covers the entire city of Chicago, focusing on major interceptors and essential hydraulic infrastructure. And for finer scale models, we concentrated on high-risk areas, like suburban scale model for the Raisin Avenue pumping station area regions, includes more detailed features, and community scale model for Chatham incorporate dual drainage and evaluates local nature-based solutions. Although I haven't yet calibrated the Chatham model due to missing field data, this setup allows for detailed analysis in critical zones without overloading computational resources. To build this model, I use SWIM. Despite some limitations in simulating basement flooding, it is still effective for surface runoff and channel flow and sewer networks. And in the nested structure, each model, the Chicago Refs and Chatham, operates independently but shares data at their boundaries to stay in sync. Currently, I'm working on a single unified nesting model that would combine all these regions into one system, allowing for natural data exchanges between scales without additional steps. But however, this approach is complex to set up and maintain due to the varying levels of detail required for each model. So using separate models can be computationally efficient for now, as each model can operate in parallel and be fine-tuned individually. And it also simplifies management, as updates or adjustments can be made to one model without impacting the others. So both approaches have their strengths, and for real-time applications like flood forecasting, managing the data, the separate operation and data exchange outside the model is still the most feasible option. So ultimately, the goal is to integrate multi-scale hydraulic modeling with cross-scale feedback that combines citywide drainage performance, infrastructure operations, and localized small-scale issues. This nested adaptive approach helps to balance computational feasibility with the need for high detail in critical areas. This video simulation shows the phase of flood dynamics we observed during the July 2nd storm. You will notice distinct phases. The system responds any early stress and partial recovery, nearing capacity, overload and failure, and finally drainage recovery. Before the July 2nd storm, a series of smaller storms left the land surface partially saturated and created antecedent conditions that increased runoff potential. By the time the storm hit, the land's infiltration capacity had already been reduced and groundwater levels were elevated. And during the event, the northern part of the area, which received more rainfall, experienced rapid runoff into the drainage system, while the southern part with more pervious area allowed for some infiltration. So this combination reduced infiltration from prior storms, elevated groundwater, and a surge in rainfall quickly overwhelmed the drainage system, leading to extensive street flooding and basement backups. You can see how the timing of peak street flooding calls align closely with flooding peaks in SWIM's prediction. Although SWIM doesn't account for basement flooding directly, its flood predictions were within half a day of actual basement flooding events. So, and also to gain additional insight into the subsurface conditions that SWIM does not account for, I use NASA's soil moisture active passive level flow data, which provides soil moisture readings every 3 hours. And SMAP data help approximate the antecedent soil moisture levels in hotspot areas and Although the resolution is pretty coarse for city application, it showed this is an approximation of groundwater recharge patterns. And the data revealed the surface soil moisture responded immediately to rainfall. And as infiltration continued, the water moved down to the root zone and eventually recharging the groundwater system. The subsequent July 5th storm, although shorter and less intense, still had a significant impact on basement flooding. This could be attributed to the lingering higher groundwater levels from the July 2nd storm, highlighting the importance of tracking subsurface saturations. So it is essential to either couple SWIM with a model that considers both surface and subsurface interactions, or to monitor root zone and groundwater levels as indicators for predicting basement flooding risk. Chicago's drainage system is highly complex and it can handle large volumes of stormwater. And to manage water levels and flows in the Chicago area waterway system, we carefully control the rate of water flowing out of the system downstream, as well as the rate of lake water entering upstream through the sluice gate. And when a storm is forecast, we take proactive steps to make room for incoming rainwater by lowering the water level in Chicago waterway system. And in a moderate storm, we increase the outflow at Lockport by opening additional sluice gates, while also closing the lake sluice gates to prevent extra water from entering. But in an extreme storm, water may enter Chicago waterway system faster than it can flow out at Lockport. So in this case, especially the river is actually flowing in both directions. But Chicago waterway system has limitations to what it can control. For instance, its operations do not affect waterways outside the system, such as the Des Plaines River and the North Branch of Chicago River, upstream of North Shore Channel. And also, this Chicago waterway system is located far downstream of these local sewers and is not directly connected to them. It cannot mitigate these upstream flooding events. Chatham has unique challenges. Several factors contribute to these flooding issues: low-lying flat terrain, impervious surfaces, climate change, and finally, aging undersized infrastructure is a significant issue. The sewers in Chatham were not built to handle the current population or today's heavier rainfalls. And Chatham sewer configuration has some unique aspect too. And Chatham sits at the top of two distinct watersheds, one flowing north to the Stickney Water Reclamation Plant and the other flowing south to Calumet. This location at the head of two watersheds provides an advantage, like Chatham sewers don't carry water from upstream communities. So this gives them an opportunity by reducing runoff through nature-based solutions or green infrastructure. And Chatham could significantly cut down on local flooding from its own home stormwater. But there's still a challenge here too, because Chatham is last in line for discharging water into shared sewer network. So when downstream communities fill the network, there's limited capacity for Chatham stormwater and wastewater to flow out. This backup leads to flooding in basement and on street. When we look closely at how sewer backups occur, this figure illustrates the mechanism that lead to backups, especially during intense rainfall. So as rain fills the sewers, some of the combined stormwater and sewage can even reach the tarp system or waterways quickly enough. Instead, the excess water has nowhere to go, resulting in a backup, and this backup pressure can push water back through the sewer system, ultimately entering streets and unprotected basement through flow drains or basement toilets. So these mechanisms show why larger scale infrastructure like TARP are essential, that are sometimes unable to prevent local flooding in neighborhoods like Chatham, emphasizing the need for additional solutions to reduce stormwater entering the sewers and during storms. Building on the mechanism of sewer backups, and the lateral connection is also can directly impact the risk of backups on individual properties. To minimize this risk, regular cleaning and maintenance of the lateral connection are essential. And proper upkeep can help keep the system flowing smoothly and reduce the chance of property level backups and during storm. While we've seen limitations of traditional sewer infrastructure in handling intense storm, another approach to managing urban flooding is through green infrastructure and nature-based solution. Chicago has been implementing various types of green infrastructure, and it's scaling up to 70 billion. And to put that into perspective, this is more than the cost of constructing the International Space Station, which was about 60 billion. Despite this large investment, the effectiveness of nature-based solutions still require further study. And this slide presents the result of our experiments evaluating the impact of various nature-based solutions on flood mitigation in Chatham. We implemented several nature-based solution interventions, including green roofs, urban forest, permeable pavement, rain gardens, vegetated swales, and wetlands to observe their effect on system performance during storm. Additionally, I examine how reductions in dry weather flow as a baseline flow of sanitary sewage in combined sewer system affecting flood risk, simulating 5%, 10%, 20%, and 40% reductions. And this floor occupied part of the sewer capacity in combined sewer system, so higher dry weather flow leaves less room for stormwater. And each NBS, each nature-based solution type affect how rainfall interacts with the landscape, often by increasing infiltration or creating additional storage. Unlike what we expect from NBS, we did not observe a delayed peak flow in this case. The reason for this involves several factors. First, the MBS measures initially capture rainfall, but under high-intensity events, they reach saturation quickly. And once saturated, they release water at a rate influenced by the overall landscape and drainage characteristics, resulting in no significant delay of peak flow. And as MBS types capture stormwater differently, they impact the shape and height of the runoff peak. Rather than delaying peak flow, MBS such as rain gardens and permeable pavement primarily reduce the volume and intensity of runoff reaching the sewer system, thereby mitigating the flood volume and the system overload. In terms of effectiveness, green roof, urban forest, and permeable pavement showed comparable impacts to reducing sanitary sewage by 20 to 40%. Meanwhile, NBS types with largest storage capacity, such as rain gardens, vegetated swales, and wetlands, proved more effective, showing impacts comparable to greater than 40% reduction in dry weather flow. To make fair comparisons, I implemented each NBS type across subcatchments with the same total volume across the Chatham area. And this approach allowed us to assess each type's functional effectiveness without varying the area of implementation. This is useful, but this approach has some limitations. Using the same volume helps isolate each NBS functional differences, but some NBS are more effective in centralized locations, or some NBS could perform better when spread across catchment. And although each NBS was implemented with the same volume, certain types may require specific conditions such as particular soil types or depths to function optimally. So this standardized approach provides useful insight, but may not fully capture each NBS performance in a varied urban landscape. By implementing each NBS type uniformly across the Chatham area, we established a benchmark for understanding each solution's potential impact. But exploring combinations or strategic placements of different NBS types could reveal more about their complementary benefits in real world. So overall, this equal volume approach served as a strong starting point, helping to identify how different NBS types compare in flood mitigation. So future studies could look into combined NBS applications and more tailored placements to optimize flood resilience. As we've explored various flood mitigation strategies and nature-based solutions, let's shift focus to the role of real-time monitoring and risk assessment in improving Chicago's flood response. The probabilistic flood risk assessment method we are developing brings together real-time data from multiple sources, integrating with predictive modeling to provide a more comprehensive view of flood risk and help manage uncertainty. And in terms of real-time monitoring, we are utilizing an extensive network of sensors, mobile observation platforms, and multi-rated multi-sensor data platform. And these tools collectively enhance flood forecasting accuracy by giving us up-to-date information on atmospheric conditions, rainfall and water levels, and flow rate across Chicago. And this real-time data then feeds into the probabilistic flood risk assessment model I'm developing, and which quantifies uncertainties in flood predictions and integrate this real-time input. And this method relies on a composite flood susceptibility map I created. And this layered approach allows us to identify high-risk areas across the city. Together, these tools provide a clear understanding of flood risk and allow for dynamic responses during flood events. And by integrating probabilistic risk assessment with real-time monitoring, we are enhancing Chicago's flood resilience, allowing for quicker and more targeted responses to protect infrastructure and communities. As we move forward, the goal is to continue refining this approach to incorporate additional data and improve models. With these advancements, we are moving toward a more adaptable and proactive flood management framework, and one that brings together historical insights, real-time monitoring, and predictive capabilities to help Chicago prepare for future flood events. To conclude, I'd like to highlight a few key take-home messages from today's presentation. First, we've seen that an integrated approach to flood mitigation, combining traditional infrastructure with nature-based solution, can be effective for reducing flood risk. And it's important to recognize the limitations within our current system. And real-time monitoring has become a critical component in flood response. And I also introduced a probabilistic flood risk assessment method, and this approach supports more adaptable, data-driven flood response framework, enhancing our capacity to manage flood risk dynamically. Finally, future directions for urban flood resilience involved continued research on combined MBS application and further real-time data integration and refining the models. By advancing our flood risk assessment methods and integrating real-time data, we can help Chicago move toward a more adaptive and proactive flood resilience. And yeah, thank you all for your attention, and I'm happy to answer any questions.
Great, thank you so much, Sunyoung. So I think in keeping with what we typically do at these seminars, we'll hand it over to Ethan for his talk first, and then do questions for both speakers at the end. So Ethan, you can take over.
Sounds good. Let's see. Let me share screen here. And then juggle. Am I getting the right screen over there? I think so.
Oh, look, perfect.
Great. Okay. Yeah. So my name is Ethan Coon. I'm a senior research scientist at Oak Ridge National Lab, and I'll talk a little bit about Southeast Texas's concerns about sort of coastal climate impacts around flooding. And I just want to sort of draw a few contrasts as we move forward between Chicago and the site we're looking at, which is Beaumont, Texas, because I think this is nice to have both of these talks paired together. It's kind of two end members of concerns that urban areas across the U.S. will be facing in the coming decades. Let's see. So this is this is obviously work from a large team. I'm leading the water theme on the Southeast Texas IFL, and so there's a bunch of people who are contributing to this work. And I just wanted to sort of call out this. This is actually starting to change. We're getting sort of our first set of turnover as people sort of leave the group and go on to bigger and better things, and also we're gaining new people. So it's sort of an exciting time as we hit that sort of 2-year mark with the project. So looking at Southeast Texas, this is sort of, if you look at this sort of picture of Texas and the star showing up here, we're northeast of Houston. I apologize. We're getting some construction going on apparently. Effectively, the area is heavily altered by sort of tropical storms, right? So this is Hurricane Harvey on the upper left. That is the interstate highway sort of coming through town. The Hurricane Imelda in 2019, you can see literally those are in fact people sitting on streetlights. You can imagine the water depths in the street that is below, but also these sort of nuisance floodings. And so this is just a standard event, that typical rainfall event that happened a couple summers ago. And this is sort of another consideration, is these sort of nuisance flooding events that are driving, big impacts on the people who are living in these areas. So the work is really motivated around this concept of compounding events. So Southeast Texas really experiences each of sort of coastally driven, sort of storm surge driven, fluvial, right? So this is like Harvey is definitely significant aspects of fluvial flooding, where sort of rain upstream is accumulating as it comes down the river and flooding a region, and then also pluvial, which is sort of what we saw in Chicago in the last talk, this sort of rain on pavement aspect of floodings, and this sort of makes it a hydrologically complex region. And it's a changing region, right? We want to think about, not just predicting and understanding what's going on today, but understanding how these changes are going or how things are going to change into the coming decade or two. And we're really thinking about that from this perspective of changing land use. So we're looking at things like changing heterogeneity and impervious surfaces, and then water structure or water infrastructure, and then changes under future climate scenarios, right? So this is both changing antecedent conditions. So maybe things will get drier, more drought, and therefore result in different effects of the subsurface, but also changing intensity and duration and frequency of tropical cyclones. And then lastly, what is the role and function of both nature-based and sort of more traditional infrastructure to reduce the impacts of flooding in these areas? So this is sort of the conceptual diagram of how we're thinking about this. And apologies to those who were at the PI meeting. This is sort of an expanded version of the talk I gave at the breakout there. But this is sort of the concept. So we're taking those three considerations for the top row, the sort of changing patterns of climate, changing patterns of tropical cyclones, then also considering changing patterns in land cover and imperviousness. This is sort of an actively growing area with a lot of industry-driven infrastructure that's sort of putting in a lot of impervious pavement and so on. And then lastly, the sort of management strategies. We really don't want to think of tomorrow's climate with today's city. We want to think about sort of tomorrow's climate with tomorrow's city. And so considering those three changes, we're then using those as input to drive high resolution, uncalibrated hydrologic models that are sort of informed and evaluated by a network of flood sensors that we hope are sort of understanding and representing our community well. And that's then being handed off to a flood inundation mapping strategy to sort of get down to the really high resolution, the sort of neighborhood scales at which people experience flooding. And then that all gets used as a tool to sort of inform this co-design of solutions that, I think everybody's sort of familiar with how these IFLs are working with the engagement aspects of things. But we want to be able to use these tools to then inform the solution process, which feeds back on sort of the infrastructure scenarios. And so we end up in this sort of design loop of design, change the forcing, model, predict our flooding, and use that to inform the co-design process. And that's really, sort of driving the process. So just sort of diving in here a little bit, this is sort of the region we're looking at. Because we're looking at hurricanes, we can't just look at sort of small localized areas. We really have to look at the full river basin. So this is the Neches River Basin in blue, that it sort of encompasses all of the blue, the red, the yellow, and the green. The sort of the big urban area to the left of this is Houston. And we're sort of sitting over here in this green area, and this is sort of Port Arthur and then Beaumont upstream of that. And so we're looking at these four separate scales to really understand the sort of different aspects of compounding flooding. We sort of have our yellow region looking at coastal flooding, our green region, which is where our biggest pluvial, sort of pavement-driven flooding is happening, and then the full river basin to think about the sort of fluvial aspects and the full basin. So how do we want to think about this stuff? And it's useful to sort of think back about how we think about flood prediction. So the National Water Model, NOAA, right? Sort of how do USGS, how do they sort of look at, for FEMA, right, response, how do they sort of look at flooding from a probabilistic perspective? And so the standard tool for this is called flood frequency analysis. And it's really a methodology that's probabilistic, right? So a 100-year storm, a 10-year storm, a 1-year storm, right? You sort of think about this from a perspective of, how likely is a given event to occur? And it's traditionally done by analyzing precipitation curves, right? And sometimes then passing those precipitation curves off to, a hydrologic model to generate peak flows in a river. Then that's filtered through a set of sort of stage curves that tell you, given a peak flow, what is the stage in the river, and that's handed off to a flooding map. And so all of these are sort of very highly parameterized, right? They're sort of empirical models, highly parameterized. And the big question is, we don't necessarily believe that these are going to stay constant in time. So we can't really rely on these existing curves and these existing data sets because of changing, climate precipitation patterns, which are going to change the sort of intensity, duration, frequency of precipitation, but also different land cover and different infrastructure, which is going to mean that sort of ratings curves are not necessarily something that we want to stay with as well. And so from early on in our proposal, we sort of decided that we were moving to a different set of models. And these models are sort of distributed, integrated hydrologic models that incorporate all of the sort of best data. But the key thing is they're really not calibrated. They're sort of the idea is we want to take the best and the sort of biggest data sets we can get, run them through these models, and then be able to sort of prognostically predict flooding from them. And so this is the code we're using is ATS, the Advanced Terrestrial Simulator, is a code that I've developed along with a large team in the Department of Energy over the last decade or so. And it brings in all these different data sets, sort of, for instance, elevation maps, land cover, soils data, geologic structure even, and obviously impervious cover, things like that. And is used to sort of inform the model. So the first domain we're going to look at here is Village Creek. This is sort of a subcatchment of the Neches Basin, and we chose it specifically because it's outside of the urban area, and so it's sort of an easier case for us to sort of do our development on. And you'll see as we move forward, we're sort of now starting to expand this approach out into the more urban areas of Beaumont and Port Arthur, which are sort of downstream of Village Creek here. And so the first thing we wanted to do was just sort of make sure that the model's performing in a reasonable way, under standard hydrologic conditions for the area. And so this is a plot of stream flow, sort of over time comparing to the National Water Model, which, the National Water Model isn't always the best model for any given area, but it's a standard, right? It's an easy way for us to sort of look at things and say, how are we doing compared to a reasonable norm of what a reasonable model ought to do? And you can see we're sort of, doing a reasonable job of capturing sort of average stream flows and typical stream flows at this sort of climatological scale that for now we're looking at sort of multiple years, out sort of a decade or so, and with daily data to drive the model. The next question then is how are we doing on peak flow, right? And so this is sort of where it gets more interesting, right? If we want to think about fluvial events, we have to be able to capture peak flows correctly. And so this is now a plot of comparing ATS evaluated with both DayMet, which is daily data, but also then stage 4, which is sort of hourly data, and evaluating the sort of peak flow aspects. And, if you look at the plots on the right, the black here is the observation. The gold and the purple are the two ATS simulations. Green is our sort of, National Water Model standard. We want to make sure we're doing at least as well as the National Water Model for these. And you can see we are. And furthermore, you can see the importance of getting the sort of high temporal resolution in order to capture peak flow, right? If you just look at the daily data, that's the gold. We're not doing a very good job of capturing the timing of the peak. But if we look at the hourly data in purple, you can see the simulations now do a much better job. And that's sort of, this is specific on the right. This is showing individual events. We did this for many events and sort of look at the statistics of this and are able to show that indeed we're sort of improving relative to the National Water Model and at this scales. So then the next question is, okay, given that we've got a model that's, sort of reasonable for this region, we want to think about how are we going to now look at the statistics of storms. And the challenge here is if we want to think about changing climate, we want to say, let's generate large numbers of events that are consistent with the current climate. Let's generate large numbers of events that are consistent with the future climate, and now change how those, and now measure how the sort of change in flooding is being experienced across these two things at different timescales. And so we're using a method called stochastic storm transposition to generate sufficient data. This is an approach that basically says, well, if you're along the coast and you're getting a hurricane, that hurricane probably could have happened over our area too. So we sort of take the precipitation patterns from one region, we move them over our basin, and we can sort of form many, thousands of storms and run through thousands of storms through our code. And the advantage of this, again, it sort of is not looking at sort of intensity, duration, frequency methods, but is saying, okay, if we can generate enough realizations, enough ensembles of storms that are consistent with a given climate, we now can generate a data set that doesn't rely on that sort of existing, intensity, duration, frequency curve. And then we want to say, okay, now we run this through a global climate model. We look at the changing patterns in these events, and we can again run under the future climate. So this is just looking at today's statistics. The rest of the, I'll talk a little bit about the future at the end of the talk, but the results here are looking at sort of consistent results that are consistent with today's climate. And so, each of these runs are then going to look like something on the right. You can sort of see the movie as this sort of very fluvial event is happening through Village Creek. And we can look at the sort of patterns now that result from this. So, we sort of summarizing what this simulation campaign looked like. This is generating now these sort of catalogs of storms, looking at antecedent conditions that are sort of selected from a seasonally appropriate case. So if the storm is happening in August, we're sort of looking at August antecedent conditions in order to capture the sort of pre-existing soil structure. And then we're simulating these sort of 5,000 events on supercomputers provided by DOE's facilities, and looking at the results. And this last bullet of planning paper is now a paper that's now published, Journal of Hydrology, from Gabriel Perez, who led this work, a postdoc with me. And the key result is basically this. So if we look at sort of the frequency of flooding, we can sort of capture what is the peak flow at the outlet of Village Creek as a function of the return interval of the given storms. And so the black data is the real data, right? So the black is sort of the last 98 years of storms that have happened. You might look at this one black dot that's sitting up here, right? That's Harvey. It's hard to know if that's right. So right, Harvey, we don't necessarily think is a 98-year storm, but we only have 98 years of record. And so that's where it sits. It might be a 500-year storm, right? And should be way off to the right. We just don't have enough data to know. So it's not really an outlier so much as it's just sort of uncertain data at that, very extreme end of storms. Red is sort of a regional is sort of a Bolton 17C USGS approach that's been standardized in USGS's strategies for looking at these. Green is a regional regression, which is another approach that's used in the literature. And you can see the sort of ATS results are showing up nicely between those two. So this is what we would do, sort of comparing to the status quo. But the nice thing with ATS is now we can look beyond just sort of peak flow and look at sort of statistics of this. So now, with each of those storms, we're able to compute what's the inundated pattern. And so on the left here, we can look at sort of what's the inundation fraction, over 10 centimeters, over 20 centimeters, over 50 centimeters, and over a meter. As compared to sort of bank full. And we can kind of look at sort of, okay, what's the return interval of a given fraction of the basin that's being flooded, and look at the statistics of that. We can also look at the sort of spatial patterns of this. So on the right here now is things like the percentage of years flooded, ranging from 20% to 100% of years where the water level was over 10 centimeters. And you can start to see, well, obviously this is a very fluvial dominated system, so the river network is really popping out here. But you can start to see that there are regions that sort of start to flood more frequently over the different conditions. And lastly, because we can do this sort of inundated area, we can also start to intersect this with population. And so this is an example simulation where we're overlaying this with LandScan, a product looking at sort of specific population locations across the basin. And you can start to see now, we can look at the statistics of how people are being affected by these storms. And so now, rather than plotting peak flow, rather than plotting inundated area against return period, we can start to look at, number of people within a flood-prone area as a function of return interval. And that's really, these are really sort of first of a kind sets of data. This isn't something that other people have been doing before. And that's pretty excited. We're excited by that. I will say, if I go back to this image for a second, you can see we're still not quite at the resolution we really would like. So this is sort of the blue. You can start to see the individual triangular elements that are happening in, away from some of these streams in some of the flooded areas. And we just don't have the sort of, 1 meter, 3 meter DEM scale resolution that we would like in order to be able to actually say, hey, this flooding is happening in this building. But you'll see in a moment, we're starting to work on that problem. So I just want to sort of provide that caveat that, I don't necessarily think that this population, result on the next plot is all that accurate yet. But I think we do sort of are getting to this strategy of being able to do this and in a feasible and realistic way. So with that, I just want to sort of summarize the last bit of this first half of this talk, and just sort of say this is sort of a new strategy that really is allowing us, that we think will allow us to look at sort of flooding under future conditions without relying on sort of empirical relationships that we don't think are necessarily going to hold under the sort of changing climate, land cover, and infrastructure. So if that's our sort of core capability that we're building out, we've built that out over the first year or two of the IFL. Now, where do we take that within the context of this sort of broader scope of diagram of informing decisions, and how do we start to put this into practice for our community? And so for the second half of the talk now, I'm just going to sort of highlight work in each of these boxes that are moving forward to this sort of broader conceptual approach that we've taken with the project. And just we're not all there yet, but we're sort of getting closer, and it's both exciting and nerve-wracking from the perspective to think that we're going to start taking this tool in the next year or two. We're going to start taking this tool and taking these results to the community members, to the task force members, and really starting to think about sort of co-design solutions. It's sort of an exciting time to sort of see these pieces starting to come together. So with the rest of this, I'll have a bunch of sort of individual slides to call out each aspect of this work now moving forward and where we're at. So the first is the sort of tropical cyclone sense. The biggest challenge here is that GCMs are simply not at a resolution that they can predict tropical cyclones. They can accurately predict hurricanes, and so we're looking at, and furthermore, we need to be able to do this with large numbers of runs. It's not like we can really sit with just a handful of WRF simulations or something like that over the North Atlantic and expect that we can get enough statistics to build out the catalogs of hurricanes that we want to be able to use to look at this. And so the approach we're taking is a sort of statistical downscaling approach, where we first say, given a GCM's output, how do we detect when a tropical cyclone could have happened? And then we're using quite simple models to sort of reconstruct the rainfall associated with following the storm across that storm track. And so this approach is sort of think of this as like a numerical weather generation, right? A numerical hurricane rainfall generator that's just allowing us to do it cheaply enough to build from these tracks enough statistics of events. On the land cover forecast, we're starting to pull these in now. This was a sort of high-risk strategy that we wanted to look at from Oak Ridge's geospatial artificial intelligence group, that they'd started to look at these sort of foundation models that basically allow you to sort of train using generative AI to sort of forecast impervious change. And so the method is a diffusion-based model, sort of conditioned on historical imperviousness and land use and land change maps. And the concept is basically taking the historical, each frame of national land cover database, can we then look forward and predict out regions of growth? And so this is run not just over Beaumont, it's run over the entire nation to get enough data to be able to think about it. But then we can start to look at sort of, okay, given the current conditions, given the history of conditions, and given how the history of how these have developed in cities like Beaumont across America, how do we think about sort of where does we start to see patterns of impervious surface pop out? And so we're really excited to start to take these now and take these projected data. So on the right, you can sort of see the different historical frames coming in, and then lastly, the sort of the current time. What is the impervious cover? And we want to start taking those and say, now, what are the implications of these for flooding? The third box across the top right was the sort of infrastructure scenarios. So we need to get the model ready to be able to take these infrastructure scenarios that are being generated by our co-design team and in sort of conjunction with the community task forces that they're working with in order to create these. And so this is now Alligator Bayou. It's sort of over Port Arthur, one of the most impervious, sort of urban regions of the area. And looking at these sort of the sort of maps of the area. So this is a heavily pumped system. This whole area is basically drained to an area where then they pump it uphill to get it out into the neighboring canal and out into the ship canal. It's protected by a series of by a levee that sort of runs along this lower right corner of the domain. You can see that all the orange dots are all the pumps that are sort of ready to pump water out over the levee as needed. And the sort of large drainage networks in blue that are all sort of surface drainage. These are streams, canals, ditches that are all running out to this one large pump at the pump station to get it out into the larger canal. So unlike Chicago, where the concern was sort of basements flooding and sewer systems, the water level is so high here that basically all of the stormwater management is done on the surface, and that sort of helps us from the perspective that a lot of this infrastructure can be detected using remotely sensed approaches. Including, this is sort of a target area for the 3D hydrography program. So USGS's new extremely high resolution sets of data. And so we've been getting really good data on the sort of canals, their elevation, sort of separating them from the sort of freshwater canals that are happening as well next to deliver fresh water to various areas in the city. And this is sort of an exciting aspect of the work as well. So you can see in red on these plots are sort of several task force focus sites. These are areas that were identified by our community as being both frequently flooded and sort of high importance to the community. And so these are the areas that they're going to start with from a perspective of co-design. And so we're starting, making sure we can represent things well in those areas. There are also sort of large infrastructure projects. So the Halbuti Halbuti detention pond is this gold patch, and it's really a very large area that sort of water from the canal is allowed to flood this sort of large basin, and then can be pumped out at a later time. So we both want to think of these sort of large infrastructure projects, but also the sort of smaller green infrastructure distributed things like green sort of rain gardens and things like that were discussed in the last talk as well. And so we sort of think about this from a modeling perspective now as a scale question. And so to represent these in ATS, we sort of split these between things that are implicit. So if you look at this plot on the right now, looking at sort of the variation of spatial scales from very small to very large, we sort of set this vertical, gray brown bar as sort of, this is the scale at which we're modeling. And so we need to be able to resolve everything on the left of that through sort of some implicit practices that we represent as subgrid models. Everything on the right we're explicitly representing in the model. And so we think about these sort of different things across these scales and how do we represent them in models. And so just a few examples of how we're doing this. I'll start in the upper right with drainage canals. You can see that as we build out these meshes, we're explicitly building in the sort of ditches and the canals. So you can sort of see the long linear structure in the lower right that is the bigger canal, and then a small feeder system that's running into the pump station is also represented. But using these sort of highly unstructured meshes, we're able to represent these canals in an extremely accurate way. Moving to the upper left, we have to think about impervious surface, and that's something that at this sort of maybe 10 to 100 meter resolution is still a subgrid process, right? This is something that we're going to have to capture fractions of imperviousness across our basin, and so we've been thinking about ways to embed those and have implemented that. On the lower left, we have sort of the stage-based pump systems and gate, and on the lower right, the gate structures that together are used at places like Halbuti. This is the picture of Halbuti now in the middle. This is sort of the very large pump system that sort of allows you to open the gate, drain the canal into this pond, and the basin that we're seeing here is really like a tiny fraction of the area that's actually filled when they start to fill this up. And then can be pumped back out. And so each of these aspects are sort of implemented in ATS, some in explicit ways like the gates and the pumps, some in implicit ways like the impervious surfaces. And then we start to run, and now this is starting to look at sort of how we incorporate this at the larger scale. Through these strategies, we're really, and through, frankly, large amounts of computing resources that are available to sort of DOE funded projects, we're able to look at sort of the full river basin, the Neches Basin here, to capture the sort of full fluvial, as we zoom in now to the red box being Alligator Bayou, this sort of heavily pumped area. You can see how Booty is starting to show up in a simulation now in the dark blue area in the middle, and some sort of pluvially driven flooding in the to the southwest of it, and also the coastal effects at this large scale. Lastly, I want to come back to a couple aspects that are allowing us to evaluate the model. So first of all, is sort of like I mentioned before, even at this sort of high resolution, if we're modeling the entire Neches Basin, we really can't resolve the sort of 1 to 3 meter DEM that's needed to capture sort of neighborhood scale flooding at the level of individual buildings. But we do think the hydrologic model is doing a good job of getting the water in the right area and getting it close, right? And so the question is, can we think of this as a multi-scale process that we can then downscale the hydrologic output from the sort of 10 to 100 meter resolution that we're modeling to sort of 1 meter DEMs. And we've looked at a variety of strategies at doing this, sort of from the left, the model output. As we move across, we have sort of hand-driven approaches, which basically take the perspective that everything's coming from the stream and allocate water based off of that, to just a direct sort of movement of water, right? Sort of fill up the low-lying areas first, which would be a very pluvial approach, which basically says, okay, we expect that the water in each triangle is right. Let's just sort of downscale it to the DEM at that resolution. And we're starting to think about sort of hybrid methods that allow us to take the best of both worlds, that near a stream is a more fluvial-driven mechanism, but away from the stream is a more pluvial-driven mechanism. And we're hopeful that these start to get now at reasonable pictures that we think we can really get at sort of building to neighborhood scale predictions. How do we evaluate this, right? So this is a big aspect is there's a large sensor network from the Southeast Texas Flood Control District that we're building upon and augmenting. And we're augmenting that with sort of additional sensors to provide this high resolution data. And also looking very closely at sort of the key areas. Now, these are each of these circles are sort of representing some of the sensors and sort of when and to what extent they're seeing various floods. But it's overlapped now with the sort of the gold regions, which were areas that were identified by our community as sort of key areas of interest to them. And so we want to start to think, how do we augment this network to make sure that we're being responsive to the community and simultaneously being able to accurately evaluate our models to make sure we trust our predictions and build confidence in our predictions. And so to do that, we're really thinking about sort of how do we, this sort of equity-informed sensor network concept. And so this is answering the question, how well are our sensors sampling the people in our communities? And this gets tricky, right? Both hydrologically and from a social science perspective. We look at each sensor, we sort of identify a region that we think the sensor is an accurate predictor for, and then we start to overlay it with things like social vulnerability indices. So these are the purple to orange shading that you're seeing here that are sort of indicating from sort of 0 being very, very low vulnerability to 3 being very high vulnerability based off of a series of, but based off of a set of considerations that are being brought into these, social vulnerability indices. And so we're really trying to rethink this sort of optimization problem, right? Where most of the time hydrologically, so these sensors are placed based off of like, okay, where is it flooding? Okay, we need a new sensor here to understand that, we're not monitoring our system well. So it's, led by scientists and engineers. And often, we sort of suspect that there's a bias there, and that sort of squeaky wheel neighborhoods maybe get the most attention. And so we're starting to think about how do we place these? And so we're working on a paper now that it's sort of describing how we've been thinking about this. And this is sort of an exciting aspect of rethinking how we place sensors for hydrologic considerations. So with that, I'll stop and we can take some questions. I just wanted to sort of leave you back with this sort of final figure. It is a really exciting time. We've sort of been working on these different components for the last couple of years, and we're starting to see these come together now in a way that I think is going to be really impactful. And so we're excited to be getting here, and we'll see how things go. I hope it doesn't all blow up in our faces. So thank you for your time, and I guess we've got some time for questions, hopefully.
Great, thanks so much, Ethan. All right, and yes, we have good 15 minutes left for questions for either Sunyoung or Ethan. So let's open up the floor.
Nobody wants to go first.
Oh, no.
So Ethan, I'll ask a question. Thanks for that great talk. Given the coastal area, have you experimented with combining your inland flows with surge modeling? So is that something that's on the planning horizon, or is that something that you're actively doing?
Yeah, I didn't mention that aspect of things. It's definitely on the planning horizon, not on the actively doing horizon, or the actively doing. Yeah, we're not actively doing it now. We had originally thought that we were going to look at the Army Corps, because they're doing this sort of large. There's this sort of many $1 million project, I think hundreds of millions, $1 billion project maybe, that is sort of the Galveston Bay to Sabine Lake project, right? That's sort of looking at building systems out across the full coast of Texas. So they've been running a lot of sort of both modeling and sort of observations of storm surge in the area. So our plan is to sort of build off of that. The other thing that we've been looking at is some of the GCMs that we're using are starting to add things that would allow them to predict storm surge accurately under events in sort of future climate. And so we're looking to collaborate with some of the sort of, for instance, if you got a chance, well, I guess you weren't at the PI meeting, but Steve Bruce is doing an early career on storm surge with E3SM. And so we're starting to think a little bit, can we collaborate with some other projects to provide us with input to do that? Obviously, the sort of wetland response, in order to be able to capture the effect of storm surge, we need to be able to accurately capture the sort of effects of wetlands from the coastal region as well. And so we do have a component that I didn't talk about in this talk that is looking at sort of wetland response and wetland health in the region as well. That's led by Ben Solman. And so, it's sort of, we're going to be able to take that. We're not doing it yet.
Yeah, and if I could ask one more question, because you have a combined surface subsurface model, have you investigated if you just cut the link and make it an event surface-based model, how much bias is built in by ignoring that exchange?
So we haven't done that, and I would like to do that. I think that's particularly, I think there are times when we could get a lot of computational speed back by simply saying, okay, we're going to track the subsurface until it's saturated, and then let's basically say, okay, stop, restart with just surface effects going on. That I think the effect of that would be quite minor. The challenge there is when we started looking at doing that from the start was, most models of flooding tend to use effective rainfall, right? They sort of start with the concept that there's going to be some fraction of the initial rainfall that's going to go into the subsurface, and we're going to throw that away. We're going to ignore that. And we just don't have, we just don't believe the curves for that. We just don't think that's a realistic way to look at it. So I think the We haven't done that yet. I would like to do that. It's definitely a numerical experiment we want to do. I think there might be opportunities to say, okay, at this point, we can really throw away the subsurface and it's not going to make a huge effect. I just don't know when.
Great. If we could, let's go to Sunyoung first to see if she wants to respond on this point.
Actually, I raised hand for asking a question to Ethan, and I'm highly interested in coupling ATS with a swim. To couple ATS with swim, I'm considering scale compatibility. And do you have any recommendations for managing the temporal and spatial scaling differences between ATS subsurface processes and swim urban drainage dynamics? And
Yeah, that's
and
I'm sorry.
yeah. And also, when operating ATS at finer scales within a larger urban model, what are the most common challenges related to the scaling issues, and how does ATS handle high resolution sub-catchment inputs or smaller urban areas without causing computational inefficiency?
Well, so I'll answer the second question first because you basically just answered it for me. It's computational resources, right? This is not a cheap concept, right? And so both because of the sort of distinct differences in scale, both spatially, if you're trying to represent sort of large spatial patterns and the high resolution, but also temporally, right? The sort of fast dynamic response of a wave moving through a pipe versus the sort of slower groundwater driven flows. I would say our approach right now is brute force. It's not necessarily as sort of mature as I would like. I mean, there are sort of scale separations that one ought to be able to say, hey, let's solve this part explicitly and this part implicitly. And I think in the future, we'd like to explore that. At this point, we rely on the fact that DOE has some big computers and we sort of let them go to work. So I don't have a good answer for you there, I guess. But the computational concern is the biggest concern. We do have sort of a limited pipe network model that we put in ATS just as a prototype for thinking about how how things could work when you start to think about the stormwater system as well. This was done by Daniil Svaetsky and his group at Los Alamos, and for the sort of Delaware River Basin. There's sort of work starting to explore that, and I think the result of that is effectively that the response of that would be very similar to what if you were trying to bring in swim as well. There's a bit of a separation of scales there, right? I showed that figure of implicit versus explicit, and it's not necessarily obvious to me that like you just want to say, let's take every swim pipe and connect it up to the corresponding grid cell that it sits in and let it rip. I think that's a good way to establish a ground truth or a standard that we want to compare to. But then I think it makes sense to start to think about upscaling the sort of swim representations to sort of be at a scale that is representable across a larger basin, or starting to decouple in a weaker way. I think thinking about other strategies. So I'd say it's an open question.
Great. Thanks, Aaron. Thanks for your patience. Over to you.
Yes, I have actually a follow-up on both Larry's question and then this discussion, because what I was going to ask is, in ATS, what's the possibility to handle some of the high degree of heterogeneity, multi-scale heterogeneity, surface and subsurface? Do you see a path forward for that?
So the concern I have is, and I think this came up a little bit at the PI meeting, is there really isn't a good map of subsurface heterogeneity in particular.
Right.
Surface heterogeneity, I feel a little bit better about. We do have strategies for thinking about surface heterogeneity. So specifically, I have a paper from a few years back looking at capturing subgrid scale depression storage style terms and things like that for heterogeneity and elevation. Thinking about impervious surface, we've been thinking a lot about heterogeneity and impervious surface, and the concept there is we've been sort of splitting it across what we would call like well-connected impervious surface, right? Impervious surface that's going to immediately drain into a ditch, that's going to immediately run into a stream network, close by, versus disconnected impervious surface where it's sort of just going to run off into the neighboring, wooded or dirt areas, right? And so we've sort of been thinking a little bit about that connectivity question. And I think that's a key consideration of the effect of the subgrid heterogeneity. But in terms of the subsurface, that's a real challenge. And I mean, like, there are a lot of ways of thinking about subsurface heterogeneity that the sort of oil companies and people like that have done a lot of thinking about doing it mathematically. But you have to have data first before you can start to think about upscaling heterogeneity in the subsurface. And so I'm not sure how to think about it.
So yeah, we have been thinking about that. I mean, clearly you need some homogenization upscaling approaches. So you need ways to identify and parameterize the subgrid scale processes. So Sunyoung has already done some of that because you can coarse grain swim. Like you can represent pipes and then represent the effects of pipes in a neighborhood, for example. But what I was thinking is that ATS could be good for the surface groundwater components, and you use that to bridge up to swim, which already works on the coarse component. What do you think of that?
Yeah, I mean, I think that's very sort of reasonable. I mean, we can run sort of individual neighborhood scales. There's no reason you can't sort of resolve. We're looking at this sort of 100-meter resolution as a sweet spot for resolving, gradients, but there's no reason you can't run in ATS at higher resolution than that over smaller domains, and start to think about upscaling ATS's predictions.
Well, so this would be a great topic for a follow-up conversation. I owe you an email on that, and I'll turn things back over to other people to ask questions.
I have a question. I also have a question for Ethan. So just now we talk a lot about resolution, and I noticed in one of your slides talking about the population error in flood prone. I noticed there's a very unusual legend about the depths with 0.1 meter to 0.2 meter, 0.2 meter to 1 meter, then 1 meter to 12 meter. So that's totally because of the resolution of your data that make the third category 1 meter directly to 12 meter.
Yeah, so that that plot is from Harvey. So that sort of the result there is from Harvey, and there's a lot of dynamic range in the data and in Harvey. I mean, it's really impossible to understate how unique Harvey. Well, I hope unique. I don't. How big of a magnitude event Harvey was. And so yeah, I mean, 12-meter water was a both predicted and frankly measured result. Maybe 12 meters might be a little high, but like there were areas that were inundated by meters of water. The plot was just made to put it on a dynamic range that we can make the plot of. But yeah, I'm not sure if Leave is on. If she has comments on sort of the largest magnitude inundated observations from the area, but it was impressive.
So basically, this is because we choose the Harvey as the input. We change
in that for that. So for that picture only, and I should be careful here. Let me just. Well, I think I have it real quick. If I can be very quick here, because I want to be precise about.
Finally, you mentioned about different strategy to make the resolution for different scenario like pluvial, fluvial. I'm thinking probably come from the resolution of the.
So to be clear on this, so the plots on the left about population, those are from the statistics of events, from many events, right? This plot on the right is not necessarily, one of the events in our 5,000 storms. One of the first things we did was just sort of looking at Harvey as a case study, and sort of looking at the aspects of the sort of scales, just sort of making sure we could represent these extremes. So the event that I'm showing on the right is not in the statistics on the left. These are totally separate simulations. So I was trying to use this as an illustrative point that when we get to this scale, there is still a scale gap between the sort of hydrologic model and ATS and the sort of high resolution DEMs that you really need in order to get to the sort of neighborhood and building scales. So this was really illustrative. It wasn't, you know.
Okay, gotcha. Okay, thank you.
All right, I see we're at time. Thank you, Sunyoung and Ethan. Great talks, great discussion. I'm sure there's more to come, but that's the whole point of this exercise, right? To open up the dialogue. So thanks for thought-provoking presentations today. I look forward to seeing everybody soon. Take care.